What's up, everybody? Today is part 2 of our NLP in Python crash course. In this video today, which is taken from a collection of courses on the DataCamp platform, you will learn all about doing sentiment analysis on text data, building recommender systems that leverage text data, reusing text data for machine learning tasks and other types of advanced operations, and a lot more. If you enjoyed these videos, make sure to like and subscribe to the channel. And if you want to take your skills to the next level and apply your skills right in the browser, make sure to check out the link in the description below. And with that, happy learning.
Welcome to this course. I'm Azadeh, a principal data scientist. In this course, we'll explore natural language processing or NLP using Up Spacy. NLP is a subfield of artificial intelligence that combines computer science and linguistics to help computers understand, analyze, and generate human language. NLP helps extract insights from unstructured data. Unstructured data, such as textual data, is information that is not organized in a predefined manner. NLP incorporates statistics, machine learning, and deep learning models to understand human language, intent, and sentiment. NLP has many applications. We will introduce 3 well-known use cases: sentiment analysis, named entity recognition, and chatbots. Sentiment analysis is the use of computers to interpret the underlying subjective tone of a piece of text and categorize it into positive, neutral, or negative classes. For example, a review about great service and affordable price is classified with a positive sentiment, while a review of a horrible experience is categorized with a negative sentiment. The next NLP use case is named entity recognition, or NER. NER is used in information extraction to locate and classify named entities in unstructured text into predefined categories. Entities are objects such as a person or a location. For example, with the phrase John McCarthy was born in September 4, 1927, NER would classify John McCarthy as the name, highlighted in blue here, and September 4, 1927 as the date, highlighted in red. Another NLP use case is text generation in chatbots. ChatGPT is an example, which is based on a transformer-based language model trained on a vast amount of unstructured text data. Now that we have learned about NLP, let's learn more about Spacy and how we can utilize it in our NLP projects. Spacy is a free and open source library for NLP in Python, which is designed to simplify building systems for information extraction. Spacy provides production-ready code widely used for NLP use cases. It supports 64+ languages, is robust, fast, and has built-in visualizers for various NLP functionalities. As the first step, we install Spacy using pip, a Python package manager. We can then download any Spacy model using a specific Python command -m spacy with a given model name. Here we choose en_core_web_sm, the smallest English model. After downloading the model, we import Spacy and create an NLP object by passing the model name in quotation marks to the spacy.load function. Spacy has multiple trained models for the English language that are available for download from spacy.io website. Now that our NLP object is ready, we can move on to reading and processing text. The loaded Spacy model NLP object can process text and convert it into a doc object, which is a container to store the processed text. The doc object contains information like tokens, linguistic annotations, and relationships about the text. We'll learn about each of these later in the chapter. Let's look at an example of processing text with Spacy. This example will use a pre-processing step known as tokenization. The first step is to read text. In this case, the string a Spacy pipeline object is created. We convert this text into a doc object by running a loaded Spacy model NLP on the text. Now we can utilize list comprehension to print all tokens of the input text by using token.text for token in doc. A token is the smallest meaningful part of a text. The process of dividing a text into a list of meaningful tokens is called tokenization. Let's learn more about the Spacy and some of its core functionalities. We previously learned that a Spacy NLP pipeline is created when we load a Spacy model. We started by importing a Spacy, then call spacy.load to return an NLP object, a Spacy language class. The language class is the text processing pipeline and applies all necessary pre-processing steps to our input text behind the scenes. After that, we can apply NLP on any given text to return a doc container. Let's learn more about the Spacy NLP pipeline. Every NLP application consists of several steps of text processing. A Spacy applies a series of pre-processing steps to the text when we call NLP, the Spacy language class. Some of the processing steps are tokenization, tagging, parsing, named entity recognition, and many others, which results in a doc container. Doc object is only one of the container classes that the Spacy supports. A Spacy uses multiple data structures to represent text data. Container classes such as doc hold information about sentences, words, and the text. Another container class is the span object, which represents a slice from a doc object. And Spacy also has a token class, which represents an individual token, like a word, punctuation symbol, etc. All the container classes are generated during the Spacy NLP processing steps. Each of the processing steps we saw in the Spacy pipeline has a well-defined task. In this course, we mostly focus on tokenizer, tagger, lemmotizer, and NER components. As shown, the tokenizer creates doc object and segment text into tokens. Then the tagger and other components add more attributes such as part of speech tags, dependency labels, and label named entities. There are many more text processing components available in Spacy, and it is important to highlight some of the other important text processing components of an NLP instance and their duties, such as language, dependency parser, and sententizer. Each component has unique features to help us process our text better. We will see more examples of each component throughout the course. We introduced tokenization earlier, but let's explore it further. Tokenization is always the first processing step in a Spacy NLP pipeline, as all other processing steps require tokens in a given text. Recall that tokenization splits a sentence into its tokens, or the smallest meaningful piece of text. Tokens can be words, numbers, and punctuation. The code segment shows the tokenization process we have seen before using a small English Spacy model. Once we apply the NLP object to the input sentence and create a doc object, we can access each token by using list comprehension and print a token's text by using .text attribute. Sentence segmentation, or breaking a text into its given sentences, is a more complex task compared to tokenization due to difficulties of handling punctuation and abbreviations. Sentence segmentation happens as part of the dependency parser pipeline component. We utilize a for loop to iterate over the sentences of "We are learning NLP. This course introduces a Spacy," using the .sense property of a doc container. Then we can use the .text attribute to access the sentence text. Lemmatization, one of the Spacy processing steps, reduces the word forms to their lemmas. A lemma is the base form of a token in which the token appears in a dictionary. For instance, the lemma of the words eats and ate is eat. Lemmatization improves the accuracy of many language modeling tasks. We iterate over tokens to get their text and lemmas using token.text and token.lemma_. Welcome back. Let's learn about some of Spacy's linguistic features such as the part-of-speech tagger and named entity recognizer to extract information from text. POS stands for part-of-speech. A part-of-speech is a grammatical term that categorizes words based on their function and context within a sentence. For example, the English language has 9 main part-of-speech categories. Some of them are verb, noun, adjective, adverb, and conjunction. One use case for part-of-speech tagging is to confirm the meaning of a word. For example, some words such as watch can be both noun and verb. Spacy captures part-of-speech tags in the POS_ feature of the NLP pipeline. Spacy.explain can be used on a given tag to include explanations of the tags. Let's look at an example for extracting part-of-speech tags for 2 sentences of I watched TV and I left without my watch. We use list comprehension to identify the token and the part-of-speech tag using token.pos_ and the explanation using spacy.explain and passing it token.pos_. The word watch is correctly tagged as a verb in the first sentence and tagged as a noun in the second example. On to named entity recognition. A named entity is a word or phrase that refers to a specific entity with a name, such as an organization. Name entity recognition, or NER, is an NLP task that classifies named entities found in an unstructured text into predefined categories such as person names. Spacy supports a wide range of entity types such as person to represent a named person, org to represent a company, GPE for a geopolitical entity like a country, LOC for other locations such as mountain ranges, date, and time. Spacy models can predict named entities and their corresponding labels as part of the NER component. Named entities are available via the doc.ents property of a doc container. Spacy will also tag each entity with its corresponding label, which represents an entity type. The label of an entity is available via the .label_ property. The code snippet illustrates how we extract named entities from Albert Einstein was genius. We can iterate through entities by using doc.ents attribute and access entity text, the start and end characters of each entity, and entity labels by using .text, .start_char, .end_char, and .label_ respectively. In this instance, Albert Einstein is detected as a person, which starts from the first and ends at the 15th character of the given text. An alternative approach to extracting entities and their types is to directly use token class instead of accessing doc.ents to only check extracted name entities. Spacy tags each token in a given doc container with its entity type if it is categorized as an entity. We can access a token's .text and .entity_type. If a token is not classified as an entity, such as the words was and genius, we will see an empty string as the entity type. We can also visualize these entities using Spacy. Displacy has different visualization options such as the Entity Visualizer, which highlights named entities and their labels in a text. For example, we can use displacy.serve function to visualize named entities of a previous example. Albert Einstein was genius. The displacy.serve function takes two arguments, a doc container and the type of displacy visualization, which is ENT or entities in this instance. Welcome. In this video, we will cover more details on part-of-speech tagging and introduce dependency parsing. We have learned how we can use Spacy to extract part-of-speech tags. Each word is tagged by a part-of-speech tag depending on its context and the other surrounding words and their part-of-speech tags. For example, given a tricky sentence such as "My cat will fish for a fish tomorrow in a fishy way," the Spacy tagger makes correct part-of-speech tag predictions for the fish and fishy words by tagging the first word fish to verb, the second word fish to noun, and the word fishy to adjective. Now, the question you might ask is, what is the importance of part-of-speech tags? Many applications need to know the word type for better accuracy. For example, in translation systems, the word fish as a verb and as a noun will map to different words in Spanish. Syntactic information such as part-of-speech tags can help many tasks further down the pipeline, such as word sense disambiguation or WSD. WSD is a classical problem of deciding in which sense a word is used in a sentence. Determining the sense of the word can be crucial in search engines, machine translation, and question answering systems. For example, for the word play, the part-of-speech tagger can help with WSD when the tagger labels the senses of the word with a noun or verb depending on its context. Let's use part-of-speech tagging for WSD. We create a tuple of the token and the .pos underscore tag by looping over each token in the doc container and check if fish is in the tokenized text. The word fish in "I will fish tomorrow" has a .pos underscore tag of a verb, which identifies its sense correctly as to catch fish. In the sentence "I ate fish," the word fish has a .pos underscore tag of noun, and it identifies the sense as an animal. We have learned part-of-speech tags, which are grammatical categories of words. Part-of-speech tags do not reveal any relation between distant words in a given sentence. This is where dependency parsing comes in. This process provides a structured way of exploring the sentence syntax. It is analyzing sentence structure via dependencies between tokens. A dependency or a dependency relation is a directed link between two tokens. The result of this procedure is always a tree. For example, for the sentence "we understand the differences," Spacy assigns a dependency label for each token such as nsubj, dobj, and det. For example, the first arc with nsubj label shows the subject and verb relationship between we and understand. A dependency label describes the type of syntactic relation between two tokens. A few of the most common dependency labels is provided in the table, such as nsubj or nominal subject, root, det or determiner, dobj or direct object, and aux or auxiliary. Let's draw our first dependency tree using displacy. We can use spacy.displacy.serve by passing two arguments, a doc container of a given text and a word of dep or dependency to display a dependency tree. In a dependency relation, one of the tokens is the parent and the other is its dependent. For example, For the dependency relation between the words the and differences, the is the dependent and the dependency label is det or det, which stands for determiner. We use .text and .dep underscore attributes of a token to access the dependency label of each of the tokens. We can also use a spacy.explain method to view definition of each dependency label. Welcome. Let's learn about word vectors. Word vectors or word embeddings are numerical representations of words that allow computers to perform complex tasks using text data. The purpose of word vectors is to allow a computer to understand words. Computers cannot understand text as is, but they can process numbers efficiently. For this reason, we'll convert words into numbers. Traditional methods such as the bag of words method take all words in a corpus and convert them into a unique number when creating word vectors. These words are then stored in a dictionary where I can be mapped to 1, got can be mapped to 2, and so on. The older methods allow a computer to understand words numerically, however, they do not enable understanding the meaning of the words. Consider an example with two sentences of I got COVID and I got coronavirus. These sentences represented as numerical arrays of 1 to 3 and 1 to 4 respectively with a bag of words model. The two sentences are identical, but they have different word embeddings. The computer does not have a certain way of knowing that the words COVID and coronavirus refer to the same thing. The model just sees these as two different words represented by two different numbers. Hence, the model is oblivious to context and semantics. But all hope is not lost. We can use recent methodologies to find word vectors that can be used to teach a computer if two words have similar meanings. Word vectors have a predefined number of dimensions. Statistical and machine learning models take into account word frequencies in a corpus and the presence of other words in similar contexts. A computer can then use this information to understand the similarity of words numerically by using vectors. For example, the table shows 7-dimensional word vectors that can help distinguish animals from houses or cats from dogs by capturing different aspects of these words from their surrounding context in a large corpus of text. There are multiple approaches to produce word vectors. Some of the most well-known algorithms are word-to-vec, glove, fast text, and transformer-based models. To process and train n-dimensional word vectors, word-to-vec and fast text use neural network architectures, while glove uses the word co-occurrences matrices, and transformer-based models use more complex architectures to train and predict word vectors. Spacy uses some of these methodologies to enable access to word vectors. Word vectors are a part of many Spacy models. However, a few of the models do not have word vectors. For instance, en underscore core underscore web underscore sm model, the small Spacy model, does not have any word vectors, while the medium-sized model en underscore core underscore web underscore md has 20,000 word vectors. We can learn about the size of the vocabulary and word vector dimensions by checking the value of NLP.meta for the keyword vectors. When using Spacy, we can only extract vectors of words that exist in a model's vocabulary. We use the NLP.vocab method of a Spacy model to access a vocabulary object. Then the NLP.vocab.strings attribute of a vocab object can be used to access word IDs in the vocabulary. Later, the vocab.vectors can be used to access word vectors of a word using its ID. For example, given a word like, we first access the mapping of the word to its ID in the vocabulary using nlp.vocab.strings within brackets the word like, then use this ID to access the corresponding word vector using nlp.vocab.vectors inside brackets extracted word ID. Welcome. Let's learn about word vectors. Word vectors or word embeddings are numerical representations of words that allow computers to perform complex tasks using text data. The purpose of word vectors is to allow a computer to understand words. Computers cannot understand text as is, but they can process numbers efficiently. For this reason, we'll convert words into numbers. Traditional methods such as the bag of words method take all words in a corpus and convert them into a unique number when creating word vectors. These words are then stored in a dictionary where I can be mapped to 1, got can be mapped to 2, and so on. The older methods allow a computer to understand words numerically, however, they do not enable understanding the meaning of the words. Consider an example with two sentences of I got COVID and I got coronavirus. These sentences represented as numerical arrays of 1 to 3 and 1 to 4 respectively with a bag of words model. The two sentences are identical, but they have different word embeddings. The computer does not have a certain way of knowing that the words COVID and coronavirus refer to the same thing. The model just sees these as two different words represented by two different numbers. Hence, the model is oblivious to context and semantics. But all hope is not lost. We can use recent methodologies to find word vectors that can be used to teach a computer if two words have similar meanings. Word vectors have a predefined number of dimensions. Statistical and machine learning models take into account word frequencies in a corpus and the presence of other words in similar contexts. A computer can then use this information to understand the similarity of words numerically by using vectors. For example, the table shows 7-dimensional word vectors that can help distinguish animals from houses or cats from dogs by capturing different aspects of these words from their surrounding context in a large corpus of text. There are multiple approaches to produce word vectors. Some of the most well-known algorithms are word-to-vec, glove, fast text, and transformer-based models. To process and train n-dimensional word vectors, word-to-vec and fast text use neural network architectures, while glove uses the word co-occurrences matrices, and transformer-based models use more complex architectures to train and predict word vectors. Spacy uses some of these methodologies to enable access to word vectors. Word vectors are a part of many Spacy models. However, a few of the models do not have word vectors. For instance, en underscore core underscore web underscore sm model, the small Spacy model, does not have any word vectors, while the medium-sized model en underscore core underscore web underscore md has 20,000 word vectors. We can learn about the size of the vocabulary and word vector dimensions by checking the value of nlp.meta for the keyword vectors. When using Spacy, we can only extract vectors of words that exist in a model's vocabulary. We use the nlp.vocab method of a Spacy model to access a vocabulary object. Then the nlp.vocab.strings attribute of a vocab object can be used to access word IDs in the vocabulary. Later, the vocab.vectors can be used to access word vectors of a word using its ID. For example, given a word like, We first access the mapping of the word to its ID in the vocabulary using nlp.vocab.strings within brackets the word like. Then use this ID to access the corresponding word vector using nlp.vocab.vectors inside brackets extracted word ID. Welcome. Let's learn how to visualize word vectors and utilize them to find similar context. We can visualize word vectors in a scatter plot to help us understand how the vocabulary words are grouped. In order to visualize word vectors, we need to project them into a two-dimensional space. We can project vectors by extracting the two principal components via principal component analysis or PCA. We won't go into further details on PCA, but it is a way to reduce a high-dimensional dataset into a dataset of fewer dimensions, two in this case. By applying PCA and projecting word vectors of words such as wonderful, horrible, apple, banana, orange, watermelon, dog, and cat in two-dimensional space, we see these words are grouped into three semantic classes: animals, fruits, and emotional context. This shows that we are moving closer to finding the meaning of the words. Now that we have seen the projected word vectors, let us learn how to use Matplotlib, Spacy, and scikit-learn packages to create such a visualization. First, we import the required libraries and load a Spacy model. Then we extract word vectors for a given list of words by using nlp.vocab.strings and nlp.vocab.vectors method. Later, we stack these vectors vertically using nlp.vstack method for PCA calculations. Since the word vectors are 300 dimension, we need to project them into two-dimensional space. We use the PCA library from scikit-learn and extract two principal components using pca.fit_transform method. We can later use these two components as x and y coordinates per word by accessing 0 and 1 indices of the transformed word vectors, and then visualize a scatter plot using plot.text and plot.show methods. Now into analogies and semantic understanding of the words. Word vectors can capture semantics and can also support vector operations such as vector addition and subtraction. A word analogy is a semantic relationship between a pair of words. There are many types of relationships such as synonymity, anonymity, and whole part relation. Some example pairs are king minus man and queen minus woman, and also walked minus walking and swam minus swimming. Word vectors can generate remarkable analogies such as gender and tense. For example, we can represent gender mapping between the king and queen as queen minus woman plus man is equal to king. We subtract woman from queen and add man instead, and we get king. Then this analogy reads as queen is to king as woman is to man. Now let us learn how we can use Spacian's vocabulary to find similar words to a given term or phrase, such as COVID. For this purpose, we first extract COVID's word vector using nlp.vocab.vectors and nlp.vocab.strings as discussed before, and convert it to a NumPy array using an np.asArray method. Then we can use nlp.vocab.vectors most underscore similar method to search among vectors of all the words in its vocabulary for 5 most similar terms. We can see similar words such as COVID-19, corona, and COVID in the output. These words are commonly present in the same context as the word COVID and are semantically similar. Spacy uses the most underscore similar function to return word IDs of the most similar terms from its vocabulary by finding the word vectors that have the minimum distance to the word vector of COVID. We then use nlp.vocab.strings inside brackets the extracted word ID to find the similar words. Welcome. Let's determine how to find semantically similar contexts using a Spacy. Semantic similarity is the process of analyzing multiple sentences to identify similarities between them. Determining semantic similarity can help us to categorize texts into predefined categories or detect relevant text or to flag duplicate content. Suppose we need to find relevant customer questions to the word price. Given a list of sentences such as, "What is the cheapest flight from Boston to Seattle?" only the first sentence is related because it contains the word cheapest. To measure how similar two pieces of text are, we need to calculate their similarity scores. Semantic similarity score is a metric that is defined over texts, where the similarity between two texts is measured using their representative word vectors. We will use cosine similarity and word vectors to measure similarity between two pieces of text. The cosine similarity of two vectors is the cosine of the angle that's created by these two vectors, and it will always have a number between 0 and 1. A larger cosine similarity metric, or closer to 1, represents more similar word vectors. We can calculate similarity scores between token objects by using the context around tokens. Let's say we want to find out whether two words of pizza and pasta from the sentences "we eat pizza" and "we like to eat pasta" are similar and what their similarity score is. We first create two doc containers per sentence and extract tokens associated to word pizza and pasta by using indices of each word. Then we use the first token similarity function to calculate the similarity score between pizza and pasta by calling token1.similarity within parentheses token2. According to the word vectors, the tokens pizza and pasta are somewhat similar and receive a similarity score of 0.685. Similarly, Spacy can calculate the similarity score of two spans of texts. We previously learned that a span is a slice from a doc container. Subsetting a doc container results in a span object. Similar to the token class, the span class also has a span.similarity method that can be used to calculate the similarity score between two spans. We can see the span objects of eat pizza and eat pasta have a much higher cosine similarity score of 0.936 and hence are a lot more similar compared to eat pizza and like to eat pasta spans with similarity score of 0.588. We can also determine whether two documents are similar using a Spacy. First, we create doc containers per document and use the first document's .similarity method to compare it to the second document. The cosine similarity for "I like to play basketball" and "I love to play basketball" is 0.975 and close to 1. This shows the strength of word vectors in understanding meanings of the words and semantic similarity. Spacy doc vectors default to an average of word vectors in a document. Lastly, we can use a Spacy to find relevant sentences to a given keyword. For example, given a list of customer questions, we can find the most relevant sentence to a given keyword such as price. Similar to token, span, and doc objects, a Spacy sentence from sentence.sense also has a dot similarity method that can be used to compare a sentence with a word vector of a keyword. We observe that the similarity score of the first question, "What is the cheapest flight from Boston to Seattle?" is the highest and hence most relevant to the keyword price. Welcome. We previously learned about Spacy pipelines. Let's explore them further. Recall that when we call NLP on a text, Spacy first tokenizes the text to produce a doc container. The doc object is then processed in several different steps known as the processing pipeline. To continue our learnings on Spacy pipelines, in this video we will explore how to create pipeline components and add them to an existing or blank Spacy pipeline. A pipeline is a sequence of pipes or pipeline components or actors on data that make alterations to the data or extract information from it. In some cases, later pipes require the output from earlier components, while in other cases, a pipe can exist entirely on its own. As an example, for a named entity recognition pipeline, 3 pipes can be used. A tokenizer pipe, which is the first processing step in Spacy pipelines, a rule-based name entity recognizer known as the entity ruler, which finds entities, and an entity linker pipe that identifies the type of each entity. Through this processing pipeline, an input text is converted to a doc container with its corresponding annotated entities. We can use the doc.ends feature to find the entities in the input text. We often use an existing Spacy model. However, in some cases, an off-the-shelf model will not satisfy our requirements. An example of this is the sentence segmentation for a long document with 10,000 sentences. To recall, sentence segmentation is breaking a text into its given sentences. Sententizer is the name of the Spacy pipeline component that performs sentence segmentation. Given a document that has 10,000 sentences, even if we use the smallest English model, the most efficient Spacy model, en_core_web_sm, the model can take a long time to process 10,000 sentences and separate them. The reason is that when calling an existing Spacy model on a text, the whole NLP pipeline will be activated, and that means that each pipe for name entity recognition to dependency parsing will run on the text. This increases the use of computational time by 100 times. In this instance, we would want to make a blank Spacy English model by using a spacy.blank within parentheses within quotation marks en, and add the sententizer component to the pipeline by using .add_pipe method of the NLP model. By creating a blank model and simply adding a sententizer pipe, we can considerably reduce computational time. The reason is that for this version of the Spacy model, only intended pipeline component or sentence segmentation will run on the given documents. Spacy allows us to analyze a Spacy pipeline to check whether any required attributes are not set. The NLP.analyze_pipes method analyzes the components in a pipeline and outputs structured information about them, like the attributes they set on the doc and token, whether they retokenize the doc, and which scores they produce during training. It also shows warnings if components require values that are not set by the previous components. For example, when the entity linker is used, but no component before entity linker sets named entities. While calling NLP.analyze_pipes method, we can also set the pretty argument to true, which will print a nicely organized table as the result of analyzing the pipeline components. The snapshot shows the results of the analyze_pipes method. While we don't go into technical details of all the fields, we are familiar with some of the components and attributes provided in this snapshot. In this case, the result of the analysis is no problems found. Welcome. Let's learn about Entity Ruler, a component in Spacy that allows us to include or modify named entities using pattern matching rules. Entity Ruler lets us add entities to doc.ends. It can be combined with Entity Recognizer, a Spacy pipeline component for name entity recognition to boost accuracy or used on its own to implement a purely rule-based entity recognition system. We can add named entities to a doc container using an entity pattern. Entity patterns are dictionaries with two keys. One key is the label, which is specifying the label to assign to the entity if the pattern is matched, and the second key is the pattern, which is the matched string. The entity ruler accepts two types of pattern: phrase entity and token entity patterns. A phrase entity pattern is used for exact string matches. For example, to exactly match Microsoft as a named entity with a label of org, we can use an entity pattern dictionary with a label equal to org or organization and the pattern to be set as Microsoft. A token entity pattern uses one dictionary to describe one token. For example, to match lowercase San Francisco to an entity type of GPE, a location type, we can use an entity pattern dictionary with a label equal to GPE and the pattern to be set to a list of two key value pairs where the key is set to lower and the value is set to San for one and Francisco for the other pair. The entity ruler can be added to a Spacy model using .add_pipe method by passing within quotation mark entity_ruler name. When the NLP model is called on a text, it will find matches in the doc container and add them as entities in the doc.ends, using the specified pattern label as the entity label. As an example, we load a blank Spacy model and use .add_pipe within parentheses within quotation mark entity ruler method to add entity ruler component. Next, we define a list of patterns. Patterns can be a combination of phrase entity and token entity patterns. These patterns can be added to the entity ruler component using .add_patterns method. Next, we run the model on a given text to generate a doc container. The NLP model uses the entity ruler component to populate the .ends attribute of the doc container. In this instance, Microsoft and San Francisco are extracted as entities with org and GPE entity labels respectively. The entity ruler is designed to integrate with the Spacy's existing components and enhance the name entity recognizer performance. Let us look at an example of Manhattan Associates is a company in the US. In this case, the model is unable to accurately classify Manhattan Associates as an org or org. We can add an entity ruler component to the current NLP pipeline. If we add the ruler after an existing NER component by setting the after argument of the .add_pipe method to NER, the entity ruler will only add entities to the doc.ends if they don't overlap with existing entities predicted by the model. In this case, the model tags Manhattan with an incorrect GPE type because the ruler component is called after existing NER or entity recognizer component of the model. However, if we add an entity ruler before the NER component by setting the before argument of .add_pipe method to NER to recognize Manhattan Associates as an org or organization, the entity recognizer will respect the existing entity spans and adjust its prediction based on patterns added to the entity ruler. This can improve model accuracy in our case. Welcome. Let's learn about rule-based information extraction. Rule-based information extraction is useful for many NLP tasks. Certain types of entities, such as dates or phone numbers, have distinct formats that can be recognized by a set of rules without needing to train any model. Regular expressions or regex are used for rule-based information extraction with complex string matching patterns. Regex can be used to retrieve patterns or replace matching patterns in a string with some other patterns. For example, given a text, we can use regular expressions to find any reference to links or phone numbers. Nearly all data scientists and engineers use regex at some stage in their workflow, from cleaning data to implementing machine learning models. There are several advantages in using regex. Due to its complex syntax, it allows programmers to write robust rules. It allows finding all types of variances in strings, performs quickly, and it is supported by different programming languages. Despite these advantages, regex has a few weaknesses. Its syntax is quite difficult for beginners. Writing good regex patterns require a knowledge of all the ways a pattern may vary in text. Python comes prepackaged with a regex library called RE. Let's assume we want to find the phone numbers in a text. The first step is to define a pattern. Assuming a phone number is always written as something like 3 digits dash 3 digits dash 4 digits, a pattern to find such phone numbers is shown. In this pattern, \d is representative of a meta character that matches any digit from 0 to 9. A number within curly brackets shows how many occurrences of the pattern are expected. Hence, parentheses \d curly brackets 3 is looking for 3 digits. We also use dash in between digits to match the shape of the phone number. To find any matching patterns in a given text, we can use re.findIter method from the RE package. We can iterate through found matches. Every match contains of a start and end characters of the matching section of the text. They are accessible using match.start and match.end methods. We can see that two phone numbers that are matching the given pattern 832-123-5555 and 425-123-4567 are found with their corresponding start and end characters from the input text. Spacy has quick ways to implement regex in 3 pipes: matcher, phrase matcher, and entity ruler. Matcher and phrase matcher do not align the match patterns as entities in a doc.ends. For this reason, we utilize entity ruler to implement regular expressions. We have already learned to use entity ruler to improve entity recognition accuracy in Spacy. We will learn more about matcher and phrase matcher later on. Let's look at an example of using entity ruler to find phone numbers. The pattern consists of a list of dictionaries with 2 keys of label and pattern. In this instance, the label is set to phone number. To match a pattern such as 3 digits dash 3 digits dash 4 digits, we use a pattern that consists of 5 smaller dictionaries, where each dictionary is representing a part of the matching pattern. The first, third, and fifth dictionaries with the key of shape are representing patterns with the shape of 3 or 4 digits by using 3 or 4 Ds. The second and fourth dictionaries with the key of ORTH are representing the exact match of a string, which is set to a dash in this pattern. Writing patterns in Spacy requires practice. Spacy documentation provides more information about different pattern attributes. Welcome! Let's learn more about rule-based information extraction using Spacy. Regex patterns are not trivial to read and debug. For these reasons, Spacy provides a readable, production-level, and maintainable alternative, the matcher class. The matcher class can match predefined rules to a sequence of tokens in doc containers. Let's look at an example. We first import Spacy and the matcher class. We then load the en_core_web_sm model and run the model on the given text to generate a doc container. Next, a matcher object is initialized with the given model's vocabulary by using matcher within parentheses NLP.vocab. Next, we define a pattern to match lowercase good and morning by defining a list with two key value pairs. The first one has a key of lower and value of good, and the second one has a key of lower and value of morning. Then we add this pattern with a custom name such as morning underscore greeting to a list of patterns in the matcher object and run the matcher on the doc container. The output of a matcher object is matched patterns which include tuples of a match ID, a start and end token indices of the matched pattern. The matcher class allows patterns to be more expressive by allowing some operators inside the curly brackets. These operators are for extended comparison and look similar to Python's in, not in, and comparison operators. The table shows a list of supported operators in the matcher class. For instance, if we want to match both lowercase good morning and good evening patterns in a text, we can use a single matching pattern and the in operator. In this case, the pattern will be a list of two key value pairs. The first one is within brackets key of lower, value of good, and the second one is within curly brackets the key of lower and value, which itself is a dictionary with a key of in and a value of a list of morning and evening. While processing unstructured text, we often have long lists and dictionaries that we want to scan and match in given text. The matcher patterns are handcrafted, and each token needs to be coded individually. If we have a long list of patterns, matcher is no longer the best option. In this instance, phrase matcher class helps us to match long dictionaries. As an example for phrase matcher, let's assume that we want to match two terms in a given text, Bill Gates and John Smith. First, we import a Spacy and phrase matcher class. Then we load the en underscore core underscore web underscore sm model and initialize the phrase matcher object using phrase matcher within parentheses nlp.vocab. Next, we create patterns for the phrase matcher object by calling the nlp.make underscore doc method on each term. This method converts given terms into pattern entities that are usable by the phrase matcher class. Then we follow similar steps as the matcher class and run the phrase matcher object on the given doc container of a text and iterate through matches to extract a start and end token IDs of the matched patterns. The previous example shows how we can match patterns by their exact values. If we want to match lowercase patterns or utilize shape of a pattern for matching, we can use the attr or attribute argument in the phrase matcher class. In one example, we set the attr argument to lower and allow phrase matcher to find lowercase matching patterns. In the second example, by setting the attr argument to shape, we are asking phrase matcher to match patterns to a given shape. In this instance, we are looking to retrieve IP addresses in a text and provide multiple examples of them, such as 110.0.0.0 to the phrase matcher class. Welcome. We have learned to use a Spacy model functionality such as part of speech taggers and NER. We'll now learn about situations where we might seek to customize Spacy models. Spacy models go a long way for general NLP use cases such as splitting a document into sentences, understanding sentence syntax, and extracting name entities. However, sometimes we seek to work on text data from specific domains that Spacy models haven't seen during their training. For example, Twitter data can contain hashtags or emotions which may not have any specific meaning outside the Twitter platform. Additionally, Twitter sentences are usually just phrases and not full sentences. As a result, We might observe low-quality sentence segmentation results for this data if we use off-the-shelf Spacy models. Similarly, text data from the medical domain typically contains several name entities such as drugs and diseases. We don't expect these entities to be classified accurately using existing Spacy NER models, because the models don't generally contain disease or drug entity labels, and they will perform poorly on such domain data. In such scenarios, it is worthwhile to train a Spacy model using our own domain-specific text data. The snapshot shows an example of a NER model results that is trained on medical domain data and hence performs well. We can usually make the model more accurate by showing it examples from our domain, and we often also want to predict categories specific to our problem. Before starting to train, we need to ask the following questions. Do Spacy models perform well enough on our data? And does our domain include many labels that are absent in the Spacy models? To determine if training is needed, let's start with the question of whether existing Spacy models perform well enough on our data. If they do, we can use existing models in our NLP pipeline. However, there are multiple scenarios where the existing models do not perform as expected. For example, an NEN Core Web SM Spacy model will not be able to correctly classify Oxford Street in "the car was navigating to the Oxford Street" as a location with a GPE label. Instead, it identifies this location as an organization with an ORG label. This is because the model did not observe similar location examples during its training phase, but might have observed Oxford in the title of organizations. Hence, it confuses this GPE entity with one that has an ORG type. If such behavior is observed from a Spacy model, we should train this Spacy model further to improve model performance. Before rushing to train our own models, we also need to confirm if there are missing output labels in the existing Spacy models or not. The snapshot shows an example of NER entities on the Common English domain on the top and an example of medical domain on the bottom. Common domain entities LOC, ORG, date that are used for training of existing Spacy models are considerably different from the medical domain entities, such as disease, dosage, chemical. It is clear that the existing Spacy models do not have many of the output labels for an NER task on medical domain data and do not perform well on our data. In such case, we'll need to first collect our domain-specific data, annotate our data, and then update an existing model or train a model from scratch with our data. Welcome! Now that we have learned how to identify whether training a Spacy model is necessary, let's learn how to prepare training data. Spacy allows us to update existing models using examples from our own annotated data. To do so, we initialize a Spacy model either with weights from an existing model or random values. Next, we predict a batch of examples with the current weights. The model then checks the predictions against the correct answers we provide and aims at optimizing the weights to achieve better results. Optimizer objects will be used in this stage. We will learn more about them later on. We then move on to the next batch of examples, and Spacy continues calling the model to predict another batch of examples in the data and refine the weights. It is clear now that the first step of training a model is always preparing training data. A Spacy model training code works with dictionaries. After collecting data, we annotate data in the required format for a Spacy model. Annotation means labeling the intent, entities, part-of-speech tags, and so on. We can see an example of an annotated data record for a NER task in the medical domain. The annotated data has two key value pairs. The first attribute records the input text with a sentence key, and the second attribute captures all the labeled entities of the input text with an entities key. In this instance, there is only one labeled entity with the entity type of medicine. Let's check another example of an annotated data record for an NER task of the common English language. In this instance, the annotated data has two entities for the given text. In such scenarios, a list of dictionaries will be stored for the entity's attribute. For example, the first element captures the Bill Gates entity with the type person, and the second element shows the SFO airport entity with the type LOC or location. The goal of data annotation is to prepare training data and point the Spacy model to what we want the model to learn. This annotated data has to be stored as a dictionary format, and we also need to provide the start and end characters of the text span with a given label. Let's see an example of a training dataset. This dataset consists of 3 example pairs for a named entity recognition task. Each example pair includes a sentence as the first element. The second element of the pair is a list of annotated entities and their corresponding start and end characters and labels. We cannot feed the raw text and annotations directly to Spacy and need to create an example object for each training example. Let's check an example for an NER model. Let's assume we have a training data point we want to feed to our NER component to ensure the model will correctly predict Austin as GPE or geopolitical entity. First, we will convert the associated text to a doc container and then use the example class from Spacy to convert the doc container and the relevant annotation to an example object, which is compatible for training with Spacy. For this purpose, we use example.fromDict method and pass two arguments, the doc container and the annotation dictionary. We can view attributes that are processed and stored at the example object by using the example.to_dict method. Welcome. Let's learn how we train Spacy models for an NER task. We previously learned that a Spacy model may not work well on a given data. One solution is to train the model on our data. In this video, we will learn how we can train a model on our data after annotating and preparing training data and by disabling all other pipeline components. For example, for training an NER component, we need to disable all other pipeline components such as Pydub speech tagger and dependency parser. We then feed our examples to the training procedure and evaluate the new NER model performance. Let's learn more about each of these steps. It is necessary to disable other pipeline components of an NLP model in order to only train the intended component. For example, if we want to train an NER model, we have to ensure any other components are disabled. For this purpose, we can use nlp.disable_pipes method given a list of other _pipes or all other pipeline components. Other _pipes is compiled by looping through each pipe name of nlp.pipe_names and checking if the pipe name is not the same as NER. In the training procedure, we will go over the training data several times. An epoch is the number of times that the learning algorithm will work through the entire training dataset. In each epoch, the training code updates the weights of the model with a small number using an optimizer object on randomly shuffled training data. Optimizers are functions that update the model weights and aim to lower the risk of errors from these predictions and improve the accuracy of the model. We can create an optimizer object using create_optimizer method. In each epoch, we first shuffle training data an example object, by using random.shuffle method. Next, for each training data point, which is a tuple of a text and annotations, we extract the equivalent dictionary object from the example object given the doc container of a text and training data annotation using example.from_dict method. The extracted example dictionary will be used to update the NLP model weights by using the NLP.update method and passing the list of the example dictionary. The optimizer object and a losses dictionary to track models lost during training. Loss is a number indicating how bad the model's prediction is on a single example. The procedure continues to process next training data points. After we have trained a model, the next step is to test the model. For this purpose, we need to save and later load it. We use the .get_pipe method to get the trained pipeline component. In an example, we trained an NER model, and hence, we get the NER component and save to the disk using the ner.to_disk method, passing a model name. Later, we load a Spacy model and create a blank NER component by using the nlp.create_pipe method. Then, we load the trained NER model from the disk by using ner.from_disk method on the created NER component. Lastly, we add the loaded NER component to the pipeline by calling nlp.add_pipe method and passing a name for the NER model, such as NER. Once a trained model is saved, it can be loaded as NLP. Then, we can use the model to find entities of a given text. We can see an example of how to apply the NER model and store entities, text, and labels for a text. Well done! We have reached the final video of this course. Let's briefly review what we have learned. In Chapter 1, we learned about NLP, some of its use cases, and how to use the Spacy pipelines to perform various natural language processing tasks, such as tokenization, sentence segmentation, and name entity recognition. In Chapter 2, we learned about linguistic features, word vectors, analogies, and word vector operations. We also learned how to use a Spacy to extract word vectors and find semantically similar terms. In the third chapter, we learned multiple approaches for rule-based information extraction using entity ruler, matcher, and phrase matcher classes in the Spacy and regex Python package. Examples of using matcher and phrase matcher are shown. And finally, we learned when we may need to train a Spacy model and how to prepare data, train Spacy models, and use trained models at inference. That was a summary of what we have learned about the Spacy. DataCamp has many useful resources for you to continue your learnings in AI and NLP. This is a list of a few recommended courses.
Hello and welcome to the course. My name is Daniel Burke and I'll be your instructor. To get started, we're first going to see how speech and audio processing is different to other kinds of data processing. Much like other data types, audio files come in many different formats, such as MP3, WAV, M4A, and FLAC. But each of these formats has a standard measure of frequency. Frequency is measured in kilohertz, but is also referred to as KHZ or sampling rate. Much like how a movie shows 30 pictures per second, which our brains register as moving pictures, the sampling rate of an audio file is a measure of the number of data chunks per second used to represent a digital sound, with 1 kilohertz equaling 1,000 pieces of information per second. For example, a song you stream will usually have a 32 kilohertz sampling rate. This means 32,000 pieces of information per second. Speech and audio books are usually between 8 and 16 kilohertz. We'll look at some of these later. And as you might have guessed, audio files are different to tabular or text data because you can't immediately see the data you're working with. To get spoken language audio files into something we can see and manipulate, we first have to open the audio file with Python's built-in wave module. We can get started with the wave module by running the command import wave. Now we have an audio file, goodmorning.wav, ready to go. It contains a person saying the words good morning. To import it, we'll use wave's open method. Now we've saved the goodmorning.wav audio file to the variable good morning in the format of a wave object. However, in this state, it's not very useful to us. To manipulate it further, we'll use the read frames method to convert the wave object to bytes. The -1 means we want to read in all of the pieces of information within the wave object. Now we've converted the audio file to bytes, what do they look like? Okay, we can see a snippet of the entire sound wave in byte form. But remember how kilohertz means thousands of pieces of information per second? The goodmorning.wav audio file is 48 kilohertz and 2 seconds long. 48,000 pieces of information per second and 2 seconds long equals 96,000 chunks of data, all for only 2 words. So if we printed out the entire sound wave in byte form, we'd see 96,000 of these combinations of letters and numbers. Don't worry if the output looks confusing for now. We'll learn how to convert these bytes into something more useful shortly. Now you can start to see how working with audio and spoken language files is different to other kinds of data. First of all, unlike text or tabular data, you can't immediately see what you're working with. So many audio files require a conversion step before you can begin working with them. And because of the frequency measure, even a few seconds of audio can contain large amounts of data. Add in background noise, other sounds, more speakers, and the number of pieces of information grows even more. We'll look into this later on. Excellent effort! You've imported the Good Morning audio file and seen what it looks like in byte form. Now, let's see if we can make those bytes even more useful. To make our audio data more useful, we're going to convert it from byte form to integers. To do this, we'll use NumPy. NumPy is a numerical Python library full of helpful functions. First, we'll import it with the common alias NP to avoid typing NumPy every time. Then, the NumPy method we'll use to convert our bytes to integers is fromBuffer. FromBuffer turns a series of data into a one-dimensional array of a specified data type. Remember, we saved the Good Morning audio file bytes to the variable soundwavegm. Since this is an array of data, we can pass it to fromBuffer as the first parameter. And then we can set the dtype parameter to the data type we'd like to get back. There are multiple data types we could pass in, but for our case, int16 is what we're after. So if we wanted to see the first values of our sound wave in integer form, what do they look like? Much better, but we're only looking at the first 10. Can you guess how long the whole array is? Remember how frequency is a measure of information per second? Our Good Morning sound wave has a frequency of 48 kilohertz, a length of 2 seconds, and thus 96,000 pieces of information. So, this array only shows the first 10 of those 96,000. Okay, we know our Good Morning sound wave has a frequency of 48 kilohertz. But what if we didn't? To find it, we could divide the length of the wave object array by the duration of the sound wave in seconds. But Python's wave module has a programmatic way. Calling getFrameWeight on a wave object will return its frame rate. Let's use it on our good morning wave object. Excellent! The method returns the number we were expecting, 48,000 or 48 kilohertz. We can use this frame rate variable for one more thing, which will be handy for visualizing our sound waves later. By dividing the number of items in the sound wave array by the frame rate, we can get the duration of our audio file. With this value, we can leverage NumPy's linspace method to figure out the timestamp where each sound wave value occurs. The linspace method takes start, stop, and num integers as parameters. Calling it will return num evenly spaced values between start and stop. Let's try it with start as 1, stop as 10, and num as 10. As you can see, it returns an array of evenly spaced numbers between 1 and 10. Let's try it on our own values to get the timestamps of pieces of information in our sound wave. Start will be 0 for the beginning of the audio file. Stop will be the length of our sound wave array over the frame rate, or in other words, the duration, and num will be the length of our sound wave array since each item in the array is a sound wave value. Let's check out the first 10 timestamps. Each of these values is the time in seconds where each sound wave byte occurred. We'll be able to use these timestamp values later to see what our sound wave looks like. It took a few conversion steps, but now you've seen what it takes to transform an audio file into numbers. Because of your efforts, we'll now be able to visualize our good morning sound wave using the plotting library matplotlib. To add to the visualization we're creating, we'll bring in another sound wave, good afternoon. This will highlight the difference between two similar sound waves and set up the intuition for the rest of the course. Both the good morning and good afternoon audio files are 48 kilohertz, or 48,000 frames per second. You'll see in future lessons, having your audio files at the same frame rate and ensuring the same data transformations are made on each of them is important. This is because if they're different, we've got the potential for data mismatches, which will prevent us from further processing. In the previous lesson, we used the frame rate to calculate the timestamps of where each piece of audio information appears. Behind the scenes, we've done the same calculations with the good afternoon audio file as the good morning file. Now we've got both sound wave arrays and timestamps ready, we can plot them. To set up a plot, we first import the matplotlib pyplot module under the common alias PLT. We can then start creating a plot by calling title on PLT and passing it a string. The string will be the title of our plot. Then we can add some labels for the X and Y axes using the X label and Y label methods. The X axis will be the timestamps we've calculated measured in seconds, and the Y axis is the amplitude, or how much the sound wave displaces air particles as it moves through the air. A value of 0 indicates no sound at all. Now we've got the plot label set up, we can add both of the sound waves. We'll make sure each of them has a label so we can differentiate them using a legend. And to make sure we can highlight the differences, we'll add an alpha parameter of 0.5 to the good morning values. This is so they appear slightly transparent on the plot. Since we've given our data labels, we can create a legend by calling the legend method on our plot. And now everything is set up, we can see our plot by calling the show method. Let's see it. Whoa, that looks nice. In the beginning, you can see how the two sound waves are similar, where the word good would be, but then they begin to differ as morning and afternoon get uttered. These differences are what we'll be working with throughout the rest of the course as we convert sound wave integers to words. To get started with spoken language recognition, let's check out the speech recognition Python library. We'll start with why the speech recognition library, and then we'll get into seeing how we can use Google's Web Speech API to transcribe speech to text. Automatic speech recognition is a tough challenge, and there's no shortage of companies and research institutions working on libraries to help solve it. There's the Sphinx library by the Carnegie Mellon University, Cowdy, speech recognition, and more. Some have more robust features than others, but they all have the same goal of transcribing audio files to text. We're going to be focused on the speech recognition library because of its low barrier to entry and its compatibility with many available speech recognition APIs we'll see shortly. We can get started with the speech recognition library by installing it from PyPy using pip and running the pip install speech recognition command in a terminal or shell. It's compatible with Python 2 and 3, but we'll be using Python 3. Now we have speech recognition installed, let's check out where all the magic happens, the recognizer class. So how do we use it? To access the recognizer class, we'll first import the speech recognition module as the abbreviation SR. Then we'll create an instance of the recognizer class by calling it from SR and assigning it to a variable recognizer. Finally, we'll set the recognizer's energy threshold to 300. The energy threshold can be thought of as the loudness of audio which is considered speech. Values below the threshold are considered silence. Values above are considered speech. A silent room is typically between 0 and 100. Speech recognition's documentation recommends 300 as a starting value, which covers most speech files. The energy threshold value will adjust automatically as the recognizer listens to an audio file. Now we've got a recognizer instance ready, it's time to recognize some speech. We chose speech recognition for its flexibility. Here's what I mean. Speech recognition has functions built in to work with many of the best speech recognition APIs. Recognize Bing accesses Microsoft's cognitive services. Recognize Google uses Google's free web speech API. Recognize Google Cloud accesses Google's cloud speech API. And Recognize Wit uses the wit.ai platform. They all accept an audio file and return text, which is hopefully the transcribed speech from the audio file. Remember, speech recognition is still far from perfect. We'll be using the Recognize Google function since it's free and doesn't require an API key. However, this limits us to 50 requests per day, and if our audio files are too long, it may time out. In my experience, I've had no issues with audio files under 5 minutes. So if you have more audio files or long audio files, you may want to look into one of the paid API services. Let's put everything together with an example. We'll start by importing the speech recognition library as SR. Then we'll initialize a recognizer class. Finally, we call Recognize Google, which takes the required parameter audio data. We can also pass it the language our audio file is in. The default language is US English. We're using a mocked version of Recognize Google for this course, so we don't go over the API limit. Running the function returns the speech detected in the audio file as text. In the last lesson, we transcribed a portion of a customer support audio file. But as you remember from earlier lessons, audio files require a bit of pre-processing before they can be worked with. Luckily, the speech recognition library has a built-in class, audio file, along with another handy method in the recognizer class, record. We can use these to take care of the pre-processing for us. It was done for us in the last lesson, but in this lesson, we'll go end to end. To begin, we import the speech recognition library and instantiate a recognizer instance as before. Then, to read in our audio file, we access the audio file class and pass it our audio file name and save it to a variable. In this case, our audio file variable is called clean support call. Now, if we check the type of clean support call, we can see it's an instance of audio file. Let's see what happens if we pass our clean support call variable to the recognize Google method. It errors, stating that the audio data parameter must be of type audio data. Our clean support call variable is currently of the type audio file. To convert it to the audio data type, we can use the recognizer class's built-in record method. Let's see it. We use a context manager, also known as with, to open and read the audio file we've saved to clean support call as source. Then we create clean support call audio using the record method and passing it source. Now, before we call recognize Google again, let's check the type of clean support call audio. Beautiful. It's an instance of audio data, just what we needed. Now our clean support call audio is in the audio data format. Let's call recognize Google and pass it our instance of audio data. Much better. Before you try it out for yourself, there are two parameters of the record method you should know about: duration and offset. The record method records up to duration seconds of audio from source, starting at offset. They're both set to none by default. This means that by default, record will record from the beginning of the file until there is no more audio. You can change this by setting them to a float value. For example, let's say you only wanted the first 2 seconds of all your audio files. You could set duration to 2. The offset parameter can be used to cut off or skip over a specified amount of seconds at the start of your audio file. For example, if you didn't want the first 5 seconds of your audio files, you could set offset to 5. These parameters could be helpful if you knew there were parts of your audio files you didn't need. But remember, altering these parameters may cut off your audio in undesired locations. The most ideal values will be found by experimentation. The speech recognition library is very powerful out of the box. However, since speech recognition is still an active area of research, there are some limitations to the library. In this lesson, we'll start exploring some of the challenges you might run into and what you can do about them. Although speech recognition is capable of transcribing audio, it doesn't necessarily know what kind of audio it's transcribing. For example, if you pass Recognizer an audio file with Japanese speech, but the language tag was English US, you'd get back the Japanese audio in English characters. That makes sense. And if you passed the same audio file with the language tag set to JA for Japanese, you'd get the audio transcribed into Japanese characters. The thing to note is, the speech recognition library doesn't automatically detect languages, so you'll have to ensure this parameter is set manually and make sure the API you're using has the capability to transcribe the language your audio files are in. We've seen the language tag in previous lessons, but what happens with non-speech audio? If we pass speech recognition an audio file of a leopard roaring, it will return an unknown value error because no speech was detected. Which also makes sense because a leopard roar, although very cool, isn't human speech. We can prevent errors by using the show all parameter. The show all parameter shows a list of all the potential transcriptions the recognize Google function came up with. In the case of our leopard raw, the list comes back empty, but we avoid raising an error. Or in the case of our Japanese file, you can see the different potential transcriptions. Next comes multiple speakers. The free Google Web API transcribes speech and returns it as a single block of text, no matter how many speakers there are. A returned single text block can still be useful. However, if your problem requires knowing who said what, you may want to consider the free API we're using as a proof of concept, and then use one of the paid versions for more complex tasks. The process of splitting more than one speaker from a single audio file is called speaker diarization. However, it is beyond the scope of this course. To get around the multiple speakers problem, you could ensure your audio files are recorded separately for each speaker. Then transcribe the individual speaker's audio. Finally, there's the problem of background noise. A rule of thumb to remember is if you have trouble understanding what has been said on an audio file due to background noise, chances are a speech recognition system will too. To try and accommodate for background noise, the recognizer class has a built-in function, adjust for ambient noise, which takes a parameter, duration. The recognizer class then listens for duration seconds at the start of the audio file and adjusts the energy threshold, or the amount the recognizer class listens, to a level suitable for the background noise. How much space you have at the start of your audio file will dictate what you can set the duration value to. The speech recognition documentation recommends somewhere between 0.5 to 1 second as a good starting point. As you know, a big part of working with data, especially audio files, is ensuring it's all in a consistent format. Pydub is a Python library made by James Robert, which provides a goldmine of tools for manipulating audio files. Becoming familiar with Pydub will give you a programmatic way to ensure your audio files are consistent and in an ideal format for transcription locally or through an API. You can install Pydub via pip by running pip install Pydub on the command line. If you're working with only WAV files, Pydub works out of the box. However, for file formats like MP3, you'll need FFmpeg, an open source audio library, which can be installed via ffmpeg.org. Once you've installed Pydub, you'll find all of its functionality is built on one main class, audio segment. To use it, we'll import it using from Pydub import audio segment. Then we can use audio segment and the from file method to import an audio file. The from file method requires the argument file, which takes a string containing an audio file's file path. In our case, wavfile.wav. The format parameter takes the target audio file's file format, but is optional as it gets inferred from the audio file name. Remember, for file types other than WAV, you'll need FFmpeg. Running this will create an instance of audio segment called WAV file of type Pydub audio segment. You'll soon see how useful this class is. Let's say you wanted to play an audio file to check its quality. You can use the play function on any audio segment. The play function requires simple audio or Pi audio for WAV files and FFmpeg for all others. Since ours is a WAV file, we'll install simple audio via pip. Then we import play from pydub.playback, and to play our audio segment instance variable, WAV file, we pass it to the play function. Running the play function will play WAV file out loud. Note, due to the limitations of the DataCamp classroom, the play function does not work on DataCamp, but will work locally. When you import a file with from file, Pydub automatically infers a number of parameters about the file. These are stored as attributes in the audio segment instance. For example, calling channels on audio segment will show you the number of channels, 1 for mono, 2 for stereo audio. Calling frame rate gives you the sample rate of your audio segment in hertz. Sample width tells you the number of bytes per sample. 1 means 8-bit, 2 means 16-bit. Max will tell you the max amplitude of your audio file, which can be considered loudness and is useful for normalizing sound levels. Finally, calling len on any audio segment will tell you the duration of the audio file in milliseconds. Having these parameters readily available is helpful to ensure all of your audio files are consistent. You can adjust them using set attribute name style functions, like set sample width to adjust the sample width, or set frame rate to change the sample rate, and set channels to alter the number of channels. Some APIs require your audio files to have certain values for these parameters. A rule of thumb is, the higher the values, excluding channels, the better. You should aim for a minimum of 16,000 Hz as the frame rate and to have your audio files in WAV format. We'll see how you can convert audio files using Pydub in a later lesson. Now you've had a little experience with Pydub and the audio segment class, in this lesson, we'll start to see just how powerful it is. Are your audio files too loud or too quiet? You can make your audio segments louder or quieter by adding or subtracting integers. Let's make our WAV file 60 decibels quieter. You'll see if you tried to transcribe audio this quiet with Recognize Google, as we saw in an earlier lesson, it would return an error. In practice, you're more likely to want to increase the volume of your audio segments. You can do this by adding an integer. This will increase your audio segment's average volume level by the same number of decibels. If your audio files are too quiet or too loud, they may produce transcription errors. As you could imagine, speech transcription works best on clear, audible speech. If you can't hear it, chances are a speech recognition system can't either. Some audio files might differ in loudness throughout. They might begin quiet and then increase in sound as a person gets comfortable talking or adjusts the microphone. The normalize function is great for taking care of this. It finds the highest level of audio throughout an audio segment and then boosts the rest of the audio up to match. You can import the normalize function via the Pydub effects module. Then, to even out the sound levels in an audio segment, you pass it to the normalize function. You can check the sound using the play function. Ensuring your file is the same loudness throughout can help with transcription. Another handy feature of audio segments is that they are sliceable and combinable. This is helpful if you need to cut down your audio files or combine them in some way. Let's say you knew your audio files had 5 seconds of static at the beginning, and you didn't want to waste compute power trying to transcribe the static. You could use slicing to remove the first 5 seconds of audio. Since audio segments are measured in milliseconds, you would do this by only keeping everything after 5,000. And then the new audio segment won't contain the 5 seconds of static. Or what if your audio file came in separate parts due to length issues or a broken recording? You can easily add 2 audio segments together using the addition operator. Operators on audio segments work in order of operation. So WAV file 1 plus WAV file 2 plus 10 will combine WAV file 1 and 2 and increase the combination by 10 decibels. If your audio files have different characteristics, combining them like this automatically scales parameters such as frame rate to be equal to the higher quality audio file. You saw in a previous lesson the issue of transcribing multiple speakers on one audio file. Well, let's say you were trying to transcribe phone calls, and using Pydub, you found your audio files are recorded in stereo format, 2 channels. Pydub allows for a stereo audio segment to split into 2 mono single channel audio segments using the split to mono function. Calling this returns a list containing each channel. Because each of these is an audio segment, you can use all of the functionality you've seen previously on them. And as long as your speakers have been recorded on separate channels, you can now transcribe their audio individually. Now you've seen how feature-rich Pydub is for manipulating audio, and you've made some changes to your files, how do you get access to your altered audio files? As you might have guessed, Pydub has a built-in method for exporting audio segments. Let's see an example. We'll first import our WAV file as usual, then we'll increase its volume by 10 decibels, and then we'll export the louder audio segment by calling the export function on it and passing it an output file path name as well as the format we'd like it to be in. The default format value for the export function is MP3, so it's important to remember to specify if you're after WAV files. In our case, we are, so we set it to WAV. Running this outputs a message letting us know our file has been exported with the specified file path name. Working with only one audio file at a time can be slow and cumbersome. You'll likely want to work with and manipulate many audio files at once. For example, say you had a folder of multiple different audio files with various audio extensions such as FLAC and MP3, but you need them in WAV. Rather than working through one by one, you could create a function for doing so. For example, the function makeWAV takes a folder path name containing wrongly formatted audio files and a folder path name to export correctly formatted audio files. Remember, you'll need FFmpeg for anything other than WAV. You might start going through the folder containing your audio files which have the wrong audio extension using Python's scandir function. Then you make sure you're only working with the files that have audio extensions MP3 and FLAC using ends with, a function which checks the end of a string. If there's a match, you could create a new file name for the file you're working with by splitting the original file name and removing its extension using os path split text and os path base name. This will leave you with the original file path without the extension, which we can add on the end with the addition operator and WAV string. Once you've got a file name to export to, you can use Pydub to import the original audio file and export it with the new file name and the updated WAV format. We'll add a print function to check what file we're creating. You could expand upon this function to manipulate the audio files as you go before exporting them. Let's see an example. During your exploratory data analysis, you find each of your audio files has 3 seconds of static at the start and are quieter than you'd like. The workflow is much the same as the previous function, except this time, to fix the problem, we start by importing each of our audio files. Then, we'll loop through each audio file, removing the first 3 seconds using slicing, then increase the volume of each file by 10 decibels using the addition operator. Once our changes have been made, we'll export the files to the WAV format. Now, our previously unideally formatted audio files are in a much better shape to be transcribed. Of course, based on the problem you're working with, there are other audio altering steps you could implement here. Luckily, Pydub makes them accessible in a simple manner. You've come a long way, from exploring an audio file from scratch, to manipulating audio files, to working with different transcription APIs. In this chapter, you're going to be putting everything you've learned together by building a proof of concept spoken language processing pipeline. Acme Studios, a technology company, has approached you to use your speech processing skills to gain insights on their customer support calls. They've sent you a handful of audio samples to explore and to see what you can find. They let you know they're not quite sure of the quality of the files or the format they're recorded in. You open the file of audio files Acme have sent through using the OS module's list_dir function and notice they're all in the MP3 format. You've seen this before, but before continuing, you decide to write down a list of things you're going to do to prepare for building the proof of concept. The first thing will be to listen to a few of the files using your media player or Pydub's play function to get an understanding of what you're working with, and then to transcribe one of them as soon as possible using Recognize Google so you have a baseline to work off. You convert the first file to WAV and transcribe it, but you know from previous work, doing this for every file is tedious. You decide it's a good idea to create functions which will help you for the rest of the proof of the concept. One to convert files to WAV format, one to find stats of an audio file using Pydub, and another to transcribe an audio file using Recognize Google. The first one, convert to WAV, takes a file path name and converts the file to a WAV file. You'll first import the file as an audio segment and then create a new file name for it using the split function on the file name and adding the .wav string extension. Finally, you'll use the export function to export it to the WAV format with the new file name similar to what you did in a previous lesson. Great! Now you can convert audio files without repeating yourself. Now, let's make one define an audio file's attributes using Pydub. Show Pydub stats takes a file name of an audio file and imports it as an audio segment. It then prints a number of attributes such as number of channels, sample width, frame rate, and more. Since you're working with customer support calls, this will help, especially with files with different numbers of channels. If there are 2 channels, you might be able to split them and transcribe each speaker separately. Finally, since you could be transcribing many audio files, you create a function to transcribe an audio file. Transcribe audio takes a file path of an audio file and creates a speech recognition recognizer instance. It transcribes the audio file using Recognize Google, as you've done in a previous lesson, and returns the transcribed text. Testing out the function on one of the calls works as expected. It reads in an audio file and returns the transcribed text. Excellent! Setting up helper functions like this at the start of a project may seem time-consuming, but they'll help save time in the long run. Now you've got some helper functions ready, it's time to start extracting information from the transcribed text. Your proposal to Acme Studios suggested sentiment analysis, the process of figuring out if text is positive, neutral, or negative would be helpful, and they agreed. Knowing the sentiment of different calls may help them figure out where customers are having the most trouble. To do sentiment analysis, you decide on using the NLTK Python library. To begin, you install NLTK using pip. Then you download the necessary NLTK packages for sentiment analysis, Punct and Veda Lexicon, using NLTK's download function. Since we don't have a large enough data set to train our own sentiment analysis model, we'll use NLTK's Veda, or Valence-Aware Dictionary and Sentiment Analyzer, as it has a pre-trained sentiment analysis model in it. Veda works by analyzing each word in a piece of text and giving it a sentiment score. It was pre-trained on social media text passages, but will lend itself well for our proof of concept. To start sentiment analysis, you import the Sentiment Intensity Analyzer class from the NLTK Veda module, and then instantiate an instance of Sentiment Intensity Analyzer and save it to the commonly named variable SID. You can find the sentiment scores of a piece of text by calling polarity scores on SID and passing it a string. Running the function will return 4 values: neg for negative, nu for neutral, pos for positive, and compound as an overall. The more negative a piece of text is, the higher the negative score will be, and the same goes for the positive score if the text is positive. If it's in the middle, neutral will be higher, and the compound value can be thought of as the overall score, with -1 being most negative and +1 being most positive. You try out the sentiment analysis on one of your transcribed phone calls using only the customer channel. Reading the transcription and comparing it to what you hear when you listen to the audio file, you can see it's not perfect. But you can see the sentiment scores are leaning in the right direction. The sentiment is fairly neutral since the customer hasn't received their product yet. From your experience with sentiment analysis, you know the sentiment can change sentence by sentence, but your current transcription function doesn't return sentences, only a large block of text. In your proposal, you mentioned this to Acme, and they allocated budget for you to try a paid transcription API. You try transcribing the same audio files using a paid API service and find it returns sentences. Using NLTK's tokenize, you break the transcription into sentences and analyze the sentiment sentence by sentence. This is helpful because it allows you to figure out which parts of the conversation the customer may be most displeased with. You can see the line where the transcription says, "This service is terrible," gets a negative compound score. Now you've done some sentiment analysis on Acme's transcribed calls, you decide named entity recognition is a good next step. Entity recognition is the process of extracting objects of interest from text. To do this, you turn to Spacy, the natural language processing library. To get started with Spacy, you can install it using pip. Once Spacy is installed, we can use Spacy's built-in language models for natural language processing by downloading them using the Spacy download command on the command line. Spacy works by turning blocks of text into docs. Docs are made up of tokens and spans. You can think of tokens as individual words and groups of tokens or sentences as spans. Let's see. First, we import Spacy, then we load the language model and save it to the conventional variable NLP. Then, to create a Spacy doc, we pass the string of text we want to use to NLP. Now we've got a Spacy doc, we can use Spacy's built-in features to find out more. You can see what token a doc contains and the index where they start using .text and .idx on objects in your doc. The number returned by IDX indicates the index of the first letter in the token. You can see where the sentences are with .sends. Here, Spacy has broken the text in our doc into sentences. Beautiful. Now let's try using Spacy's named entity recognition. A named entity is an object which is given a name, such as a person, product, location, or date. Spacy has several of these named entities built in. It can recognize straight away. You can access the named entities in a doc using .ents. Let's try. .text shows us the token that the label belongs to, and .label_ gives us the named entity label of the text. You can see Sydney is given GPE for geopolitical entity. Spacy's built-in named entities are excellent, but depending on your problem, you'll probably want to develop some of your own. Since Acme is a technology company, you decide it's a good idea to create a custom entity recognizer for their products. To do so, you can use Spacy's pipeline class, Entity Ruler. A pipeline is what Spacy uses to parse text in a doc. You can see the current pipeline you're using by calling pipeline on NLP. In our case, our pipeline has 3 steps: a tagger, a parser, and NER for named entity recognition. The Entity Ruler class allows us to create another step in the pipeline. We start by making an instance of Entity Ruler called Ruler, passing it NLP. Then we use add patterns to add the token pattern we'd like Spacy to consider an entity. In our case, we want the smartphone token to have the entity label product. We can add this rule to the pipeline before NER so we can be sure it gets used. Now, we check our pipeline, we've got a new step called Entity Ruler. Let's try it with our doc from before. You can see the token smartphone has the product named entity label. Acme are impressed with your work so far and have sent over 2 folders full of phone call audio snippets. And they've manually labeled them with pre-purchase if the customer was calling before a purchase, or post-purchase if the customer was calling after making a purchase. They said the process of labeling audio files was labor-intensive and want to know if machine learning can help. You immediately start to think of building an sklearn text classifier, and that's what we'll be doing in this lesson. You inspect the folders by importing OS and using the listdir function on the folder path. You notice there's about 50 files in each, but they're in the MP3 format. Luckily, you built a function to handle this earlier. Using your convert to WAV function you built earlier, you convert all the files from MP3 to WAV. Excellent! Now they're all in WAV format, you decide to create a function, create text list, to transcribe all of the files in a folder to text. You start with an empty list. Then, looping through the folder, if a file ends with a WAV extension, you pass the file path to your transcribe audio function, which returns the text. Once you have the text, you append it to your empty list and then return the list full of transcribed text. Running the function on the post-purchase folder returns a list of text. Let's see what the first 5 look like. Okay, we're making progress. Those helper functions came in handy. To make building your text classifier easier, you decide to put all the text into a pandas data frame. You start by importing pandas as PD, then create a post-purchase data frame by passing PD data frame a dictionary with a key named labeled, which has a value of post-purchase, and a text key whose value is the text list. You do the same for the pre-purchase text. And to have everything in one place, you combine the 2 data frames with pd.concat. Let's see it. Beautiful! Now you've got your data in a data frame. You can use it to build a text classifier with sklearn. We'll start by importing the necessary packages. NumPy is NP, pipeline from sklearn's pipeline module, multinomial NB from sklearn's naive Bayes module for our classifier, count vectorizer and TF-IDF transformer from sklearn's text feature extraction module to transform our text into numbers, and train test split to split our data into training and test sets. To start, we'll use train test split to split the data using a test size of 30%, where our X value is the text column and our Y value is the label column of the data frame we created earlier. Next, you set up a classifier pipeline as text classifier, which uses count vectorizer and TF-IDF transformer to transform each of the test samples into a certain value depending on the words they contain. Then, Multinomial NB builds a naive Bayes model to classify each sample. To train the model, you call the fit function on your text classifier and pass it the training data. Once you've got a trained model, you can evaluate it by calling the predict function on your classifier and passing it the test set data. Then you can use NumPy to compare the predictions to the test data labels. That's not a bad model. Not so naive after all. Congratulations, you've made it to the end. What a journey it's been. We started by turning audio files into sound waves using Python and NumPy. Then we transcribed speech into text using the speech recognition library and experienced some of the challenges with speech recognition, like different speakers and languages. You then learned how to manipulate and prepare audio files for transcription using Pydub. Finally, you built a proof of concept speech processing pipeline with sentiment analysis using NLTK, named entity recognition using Spacy, and text classification using sklearn. If you're after more, I suggest you try using what you've learned to build a speech processing app of your own. We weren't able to use speech recognition's microphone class in the DataCamp classroom, but you could try use it locally. Before you go, there's one more audio file to transcribe. It's called congratulations.wav. Let's see what it says. Well, I couldn't have said it better. You've just taken the first steps to becoming a spoken language processing engineer. You should be proud.
Welcome to Feature Engineering for NLP in Python. I am Ronak and I will be your instructor for this course. In this course, you will learn to extract useful features out of text and convert them into formats that are suitable for machine learning algorithms. For any ML algorithm, data fed into it must be in tabular form and all the training features must be numerical. Consider the iris dataset. Every training instance has exactly 4 numerical features. The ML algorithm uses these 4 features to train and predict if an instance belongs to class Iris virginica, Iris setosa, or Iris versicolor. ML algorithms can also work with categorical data provided they are converted into numerical form through one-hot encoding. Let's say you have a categorical feature sex with 2 categories, male and female. One-hot encoding will convert this feature into 2 features, sex male and sex female, such that each male instance has a sex male value of 1 and sex female value of 0. For females, it is the vice versa. To do this in code, we use pandas getDummies function. Let's import pandas using the alias pd. We can then pass our data frame df into the pd.getDummies function and pass a list of features to be encoded as the columns argument. Not mentioning columns will lead pandas to automatically encode all non-numerical features. Finally, we overwrite the original data frame with the encoded version by assigning the data frame returned by getDummies back to df. Consider a movie reviews dataset. This data cannot be utilized by any machine learning or ML algorithm. The training feature review isn't numerical. Neither is it categorical to perform one-hot encoding on. We need to perform 2 steps to make this dataset suitable for ML. The first is to standardize the text. This involves steps like converting words to lowercase and their base form. For instance, reduction gets lowercased and then converted to its base form reduce. We will cover these concepts in more detail in subsequent lessons. After pre-processing, the reviews are converted into a set of numerical training features through a process known as vectorization. After vectorization, our original review dataset gets converted into something like this. We will learn techniques to achieve this in later lessons. We can also extract certain basic features from text. It may be useful to know the word count, character count, and average word length of a particular text. While working with niche data such as tweets, it may also be useful to know how many hashtags have been used in a tweet. This tweet by Silverado Records, for instance, uses to. So far, we have seen how to extract features out of an entire body of text. Some NLP applications may require you to extract features for individual words. For instance, you may want to do part of speech tagging to know the different parts of speech present in your text as shown. As an example, consider the sentence, I have a dog. POS tagging will label each word with its corresponding part of speech. You may also want to know how to perform named entity recognition to find out if a particular noun is referring to a person, organization, or country. For instance, consider the sentence, Brian works at Datacamp. Here, there are two nouns, Brian and Datacamp. Brian refers to a person, whereas Datacamp refers to an organization. Therefore, broadly speaking, this course will teach you how to conduct text pre-processing, extract certain basic features, word features, and convert documents into a set of numerical features using a process known as vectorization. In this video, we will learn to extract certain basic features from text. While not very powerful, they can give us a good idea of the text we are dealing with. The most basic feature we can extract from text is the number of characters, including white spaces. For instance, the string I don't know has 13 characters. The number of characters is the length of the string. Python gives us a built-in len function which returns the length of the string passed into it. The output will be 13 here too. If our data frame df has a textual feature, say review, we can compute the number of characters for each review and store it as a new feature numchas by using the pandas data frame apply method. This is done by creating df of numchas and assigning it to df of review.apply len. Another feature we can compute is the number of words. Assuming that every word is separated by a space, we can use a string split method to convert it into a list where every element is a word. In this example, the string Mary had a little lamb is split to create a list containing the words Mary, had, a, little, and lamb. We can now compute the number of words by computing the number of elements in this list using len. To do this for a textual feature in a data frame, we first define a function that takes in a string as an argument and returns the number of words in it. The steps followed inside the function are similar as before. We then pass this function word count into apply. We create df of numwords and assign it to df of review.apply word count. Let's now compute the average length of words in a string. Let's define a function avg word length which takes in a string and returns the average word length. We first split the string into words and compute the length of each word. Next, we compute the average word length by dividing the sum of the lengths of all words by the number of words. We can now pass this into apply to generate an average word length feature like before. When working with data such as tweets, it may be useful to compute the number of hashtags or mentions used. This tweet by Datacamp, for instance, has one mention, Upendra35, which begins with an @ and two hashtags, PySpark and Spark, which begin with a hash. Let's write a function that computes the number of hashtags in a string. We split the string into words. We then use list comprehension to create a list containing only those words that are hashtags. We do this using the starts with method of strings to find out if a word begins with hash. The final step is to return the number of elements in this list using len. The procedure to compute number of mentions is identical except that we check if a word starts with @. Let's see this function in action. When we pass a string @JaneDoe, this is my first tweet, #first tweet, #happy, the function returns 2, which is indeed the number of hashtags in the string. There are other basic features we can compute, such as the number of sentences, number of paragraphs, number of words starting with an uppercase, all capital words, numeric quantities, etc. The procedure to do this is extremely similar to the ones we've already covered.
In this lesson, we will look at a set of interesting features known as readability tests. These tests are used to determine the readability of a particular passage. In other words, it indicates at what education level a person needs to be in order to comprehend a particular piece of text. The scale usually ranges from primary school up to college graduate level and is in context of the American education system. Readability tests are done using a mathematical formula that utilizes the word, syllable, and sentence count of the passage. They are routinely used by organizations to determine how easy their publications are to understand. They have also found applications in domains such as fake news and opinion spam detection. There are a variety of readability tests in use. Some of the common ones include the flesh reading ease, the gunning fog index, the simple measure of gobbledygook or smog, and the Dale-Schall score. Note that these tests are used for texts in English. Tests for other languages also exist that take into consideration the nuances of that particular language. For the sake of brevity, we will cover only the first two scores in detail. However, once you understand them, you will be in a good position to understand and use the other scores too. The flesh reading ease is one of the oldest and most widely used readability tests. The score is based on two ideas. The first is that the greater the average sentence length, the harder the text is to read. Consider these two sentences. The first is easier to follow than the second. The second is that the greater the average number of syllables in a word, the harder the text is to read. Therefore, I live in my home is considered easier to read than I reside in my domicile on account of its usage of lesser syllables per word. The higher the flesh reading ease score, the greater is the readability. Therefore, a higher score indicates that the text is easier to understand. This table shows how to interpret the flesh reading ease scores. A score above 90 would imply that the text is comprehensible to a 5th grader, whereas a score below 30 would imply the text can only be understood by college graduates. The gunning fog index was developed in 1954. Like flesh, this score is also dependent on the average sentence length. However, it uses percentage of complex words in place of average syllables per word to compute its score. Here, complex words refer to all words that have 3 or more syllables. Unlike flesh, the formula for gunning fog index is such that the higher the score, the more difficult the passage is to understand. The index can be interpreted using this table. A score of 6 would indicate 6th grade reading difficulty, whereas a score of 17 would indicate college graduate level reading difficulty. We can conduct these tests in Python using the Readability Metrics library. In order to use this package, we first need to download the punc module from NLTK. We then import the readability class from readability. Next, we create a readability object and pass in the passage or text we are evaluating. To compute a readability score, we call a method that computes the score of our interest. For instance, gunning fog. We store this variable in a variable named gf. Next, we access the score using gf.score. In this example, the text that was passed is between the reading level of a college senior and that of a college graduate.
In NLP, we usually have to deal with text from a variety of sources. For instance, it can be a news article where the text is grammatically correct and proofread. It could be tweets containing shorthands and hashtags. It could also be comments on YouTube where people have a tendency to abuse capital letters and punctuations. It is important that we standardize these texts into a machine-friendly format. We want our models to treat similar words as the same. Consider the words dogs and dog. Strictly speaking, they are different strings. However, they connotate the same thing. Similarly, reduction, reducing, and reduce should also be standardized to the same string regardless of their form and case usage. Other examples include don't and do not, and won't and will not. In the next couple of lessons, we will learn techniques to achieve this. The text processing techniques you use are dependent on the application you're working on. We'll be covering the common ones, including converting words into lowercase, removing unnecessary white space, removing punctuations, removing commonly occurring words or stop words, expanding contracted words like don't, and removing special characters such as numbers and emojis. To do this, we must first understand tokenization. Tokenization is the process of splitting a string into its constituent tokens. These tokens may be sentences, words, or punctuations and is specific to a particular language. In this course, we will primarily be focused with word and punctuation tokens. For instance, consider this sentence. Tokenizing it into its constituent words and punctuations will yield the following list of tokens. Tokenization also involves expanding contracted words. Therefore, a word like don't gets decomposed into two tokens, do and n'3, as can be seen in this example. To perform tokenization in Python, we will use the Spacy library. We first import the Spacy library. Next, we load a pre-trained English model, en core web sm, using spacy.load. This will return a language object that has the know-how to perform tokenization. This is stored in the variable NLP. Let's now define a string we want to tokenize. We pass the string into NLP to generate a Spacy doc object. We store this in a variable named doc. This doc object contains the required tokens and many other things, as we will soon find out. We generate the list of tokens by using list comprehension as shown. This is essentially looping over doc and extracting the text of each token in each iteration. The result is as follows. Lemmatization is the process of converting a word into its lowercase base form or lemma. This is an extremely powerful process of standardization. For instance, the words reducing, reduces, reduced, and reduction, when lemmatized, are all converted into its base form reduce. Similarly, be verbs such as am, are, and is are converted into be. Lemmatization also allows us to convert words with apostrophes into their full forms. Therefore, n''t is converted to not, and ve is converted to have. When you pass the string into NLP, Spacy automatically performs lemmatization by default. Therefore, generating lemmas is identical to generating tokens, except that we extract token.lemma_ in each iteration inside the list comprehension instead of token.text. Also, observe how Spacy converted is into pron. This is standard behavior where every pronoun is converted into the string pron. Once we understand how to perform tokenization and lemmatization, performing the text preprocessing techniques described earlier becomes easier. Now that we know how to convert a string into a list of lemmas, we are now in a good position to perform basic text cleaning. Some of the most common text cleaning steps include removing extra white spaces, escape sequences, punctuations, and special characters such as numbers and stop words. In other words, it is very common to remove non-alphabetic tokens and words that occur so commonly that they are not very useful for analysis. Every Python string has an isAlpha method that returns true if all the characters of the string are alphabets. Therefore, dog.isAlpha will return true, but 3dogs.isAlpha will return false as it has a non-alphabetic character 3. Similarly, numbers, punctuations, and emojis will all return false too. This is an extremely convenient method to remove all lemmatized tokens that are or contain numbers, punctuations, and emojis. If isAlpha as a silver bullet that cleans text meticulously seems too good to be true, it's because it is. Remember that isAlpha has a tendency of returning false on words which we would not want to remove. Examples include abbreviations such as USA and UK which have periods in them, and proper nouns with numbers in them such as word2vec and x to 10x. For such nuanced cases, isAlpha may not be sufficient. It may be advisable to write your own custom functions, typically using regular expressions, to ensure you're not inadvertently removing useful words. Consider the string here. This has a lot of punctuations, unnecessary extra white space, escape sequences, numbers, and emojis. We will generate the lemmatized tokens like before. Next, we loop through the tokens again and choose only those words that are either prawn or contain only alphabetic characters. Let's now print out the sanitized string. We see that all the non-alphabetic characters have been removed and each word is separated by a single space. There are some words in the English language that occur so commonly that it is often a good idea to just ignore them. Examples include articles such as and the, be verbs such as is and am, and pronouns such as he and she. Spacy has a built-in list of stop words which we can access using spacy.lang.en.stopwords.stopwords. We make a small tweak to a_lemma's generation step. Notice that we have removed the prawn condition as pronouns are stop words anyways and should be removed. Additionally, we've introduced a new condition to check if the word belongs to Spacy's list of stop words. The output is as follows. Notice how the string consists only of base form words. Always exercise caution while using third-party stop word lists. It is common that an application finds certain words useful that may be considered a stop word by third-party lists. It is often advisable to create your own custom stop word lists. There are other pre-processing techniques that are used but have been omitted for the sake of brevity. Some of them include removing HTML or XML tags, replacing accented characters, and correcting spelling errors and shorthands. We've covered a lot of text pre-processing techniques in the last couple of lessons. However, a word of caution is in place. The text pre-processing techniques you use is always dependent on the application. There are many applications which may find punctuations, numbers, and emojis useful, so it may be wise to not remove them. In other words, using all caps may be a good indicator of something. Remember to always use only those techniques that are relevant to your particular use case. In this lesson, we will cover part of speech tagging, which is one of the most popularly used feature engineering techniques in NLP. Part of speech tagging, or POS tagging, has an immense number of applications in NLP. It is used in word sense disambiguation to identify the sense of a word in a sentence. For instance, consider the sentences, "The bear is a majestic animal," and "Please bear with me." Both sentences use the word bear, but they mean different things. POS tagging helps in identifying this distinction by identifying one bear as a noun and the other as a verb. Consequentially, POS tagging is also used in sentiment analysis, question answering systems, and linguistic approaches to detecting fake news and opinion spam. For example, one paper discovered that fake news headlines on average tend to use lesser common nouns and more proper nouns than mainstream headlines. Generating the POS tags for these words proved extremely useful in detecting false or hyperpartisan news. So, what is POS tagging? It is the process of assigning every word or token in a piece of text its corresponding part of speech. For instance, consider the sentence, Jane is an amazing guitarist. A typical POS tagger will label Jane as a proper noun, is as a verb, an as a determiner or an article, amazing as an adjective, and finally, guitarist as a noun. POS tagging is extremely easy to do using Spacy's models, and performing it is almost identical to generating tokens or lemmas. As usual, we import the Spacy library and load the EN-Core WebSM model as NLP. We will use the same sentence, Jane is an amazing guitarist, from before. We will then create a doc object that will perform POS tagging by default. Using list comprehension, we generate a list of tuples, POS, where the first element of the tuple is the token and is generated using token.text. And the second element is its POS tag, which is generated using token.pos underscore. Printing POS will give us the following output. Note how the tagger correctly identified all the parts of speech as we had discussed earlier. That said, remember that POS tagging is not an exact science. Spacy infers the POS tags of these words based on the predictions given by its pre-trained models. In other words, the accuracy of the POS tagging is dependent on the data that the model has been trained on and the data that it is being used on. Spacy is capable of identifying close to 20 parts of speech, and as we saw in the previous slide, it uses specific annotations to denote a particular part of speech. For instance, prop n referred to a proper noun and det referred to a determinant. You can find the complete list of POS annotations used by Spacy in Spacy's documentation. Here is a snapshot of the page. The final technique we will learn as part of this chapter is named entity recognition. Named entity recognition, or NER, has a host of extremely useful applications. It is used to build efficient search algorithms and question answering systems. For instance, let us say you have a piece of text and you ask your system about the people that are being talked about in the text. NER would help the system in answering this question by identifying all the entities that refer to a person in the text. NER has also found application with news providers who use it to categorize their articles and customer service centers who use it to classify and record their complaints efficiently. Let us now get down to the definitions. A named entity is anything that can be denoted with a proper name or a proper noun. Named entity recognition, or NER, therefore, is the process of identifying such named entities in a piece of text and classifying them into predefined categories such as person, organization, country, etc. For example, consider the text, John Doe is a software engineer at Google. He lives in France. Performing NER on this text will tell us that there are three named entities. John Doe, who is a person, Google, which is an organization, and France, which is a country or a geopolitical entity. Like POS tagging, performing NER is extremely easy using Spacy's pre-trained models. Let's try to find the named entities in the same sentence we used earlier. As usual, we import the Spacy library, load the required model, and create a doc object for the string. When we do this, Spacy automatically computes all the named entities and makes it available as the ENTS attributes of doc. Therefore, to access the named entity and its category, we use list comprehension to loop over doc.ents and create a tuple containing the entity name, which is accessed using ent.text, and entity category, which is accessed using ent.label underscore. Printing this list out will give us the following output. We see that Spacy has correctly identified and classified all the named entities in this string. Currently, Spacy's models are capable of identifying more than 15 different types of named entities. The complete list of categories and their annotations can be found in Spacy's documentation. Here is a snapshot of the page. In this chapter, we have used Spacy's models to accomplish several tasks. However, remember that Spacy's models are not perfect and its performance depends on the data it was trained with and the data it is being used on. For instance, if you're trying to extract named entities for text from a heavily technical field such as medicine, Spacy's pre-trained models may not perform such a great job. In such nuanced cases, it is better to train your own models with your specialized data. Also, remember that Spacy's models are language specific. This is understandable considering that each language has its own grammar and nuances. The EN Core Web SM model that we have been using is, as the name suggests, only suitable for English texts. In this chapter, we will cover vectorization, which is, as you may recall, the process of converting text into vectors. Recall that for any ML algorithm to run properly, data fed into it must be in tabular form and all the training features must be numerical. This is clearly not the case for textual data. In this lesson, we will learn a technique called bag of words that converts text documents into vectors. The bag of words model is a procedure of extracting word tokens from a text document, henceforth we will refer to this as just document, computing the frequency of these word tokens, and constructing a word vector based on these frequencies and the vocabulary of the entire corpus of documents. This is best explained with the help of an example. Consider a corpus of 3 documents. The lion is the king of the jungle. Lions have an average lifespan of 15 years, and the lion is an endangered species. We now extract the unique word tokens that occur in this corpus of documents. This will be the vocabulary of our model. In this example, the following 15 word tokens will constitute our vocabulary. Since there are 15 words in our vocabulary, our word vectors will have 15 dimensions, and each dimension's value will correspond to the frequency of the word token corresponding to that dimension. For instance, the second dimension will correspond to the number of times the second word in the vocabulary and occurs in the document. Let's now convert our documents into word vectors using this bag of words model. The lion is the king of the jungle is converted to the following vector. Similarly, the other 2 sentences have the following word vector representations. As we were constructing this model, you may have noticed how text pre-processing would have been extremely useful in creating arguably better models. We would usually want lions and lion to mean the same thing and therefore counted as the same thing. The same applies to the with different cases. We would also want to remove punctuations and stop words as they are extremely common and don't really contribute much to the character of the document. Performing text pre-processing usually leads to smaller vocabularies, which is a good thing. While working with vectorization, it is routine to form word vectors running into thousands of dimensions, and keeping this to a minimum helps improve performance. To construct the bag of words model in Python, we will use the scikit-learn library. We will use the corpus from before, consisting of the 3 sentences on lions. Let's ignore text pre-processing for now. We import the text count vectorizer class from sklearn.featureextraction.text. This is the class that will help us build our bag of words model. Next, we instantiate a count vectorizer object, vectorizer. We finally create a matrix of word vectors by passing corpus to the fit transform method of vectorizer. This is stored in BOW matrix. This BOW matrix is a sparse matrix and we can print out its 2D array form using BOW matrix.toArray. This gives us the following output. Notice how this is different from the word vectors we generated. This is because count vectorizer automatically lowercases words and ignores single character tokens such as a. Also, it doesn't necessarily index the vocabulary in alphabetical order. We will learn how to map the vocabulary to the indices in the exercises. We can now use this BOW matrix as our training features in ML models. In this lesson, we will walk through a machine learning problem that utilizes feature engineering techniques we've learned to arrive at a desired result. Let's take a look at the spam filtering problem. We're given a data set of messages that have been labeled as spam or ham. Here, you can see a typical spam and ham message. Our task is to train an ML model that can predict the label given a particular text. There are 3 steps involved. The first is to pre-process the text. Next, we proceed to build the bag of words model. Finally, we conduct predictive modeling using the generated BOW vectors. Note that although we use the term modeling in the context of both BOW and machine learning, they mean 2 different things. We've already learned how to conduct text pre-processing using Spacy. However, it is also possible to do this using count vectorizer. Count vectorizer takes in a number of arguments to perform pre-processing. The lowercase argument, when set to true, converts words to lowercase. The strip accents argument can convert accented characters according to Unicode or ASCII mapping. Passing in a stop words argument will lead to count vectorizer ignoring stop words. You can pass in a custom list or the string English to use scikit-learn's list of English stop words. You can specify tokenization using a regular expression as the value of the token pattern argument. Tokenization can also be specified using a tokenizer argument. Here, you can pass a function that takes a string as an argument and returns a list of tokens. This way, count vectorizer allows usage of Spacy's tokenization techniques. Count vectorizer cannot perform certain steps such as lemmatization automatically. This is where Spacy is useful. Although it performs tokenization and pre-processing, count vectorizer's main job is to convert a corpus into a matrix of numerical vectors. As usual, we import count vectorizer from scikit-learn. We then instantiate a count vectorizer object called vectorizer. We perform accent stripping using ASCII mapping and remove English stop words. We also set the lowercase argument to false. This is because spam messages usually tend to abuse all capital words, and we might want to preserve this information for the ML step. The dataset has already been loaded into the data frame DF. We split this dataset into training and test sets using scikit-learn's train test split function. We now fit the vectorizer on the training set and transform it into its bag of words representation. We can perform both these steps together using the fit transform method. Next, we transform the test set into its BOW representation. Note that we do not fit the vectorizer with the test data. It is possible that there are some words in the test data that is not in the vocabulary of the vectorizer. In such cases, Count Vectorizer simply ignores these words. We're now in a good position to train an ML model. We will use the multinomial naive Bayes classifier for this task. We import the multinomial NB class from scikit-learn and create an object named CLF. We then fit the training BOW vectors and their corresponding labels to CLF. We can now test the performance of our model. We compute the accuracy of our model on the test set using clf.score. In this case, our model registered an accuracy of 76% on the test set. We already know how to build bag of words representations of our documents and use it to conduct various machine learning tasks. Consider the following mini reviews. One is a positive review which states that the movie was good and not boring. The other is negative, commenting that the movie was not good and boring. If we were to construct BOW vectors for these reviews, we would get identical vectors since both reviews contain exactly the same words. And herein lies the biggest shortcoming of the bag of words model. Context of the words is lost. In this example, the position of the word not changes the entire sentiment of the review. Therefore, in this lesson, we will study techniques that will allow us to model this. An n-gram is a contiguous sequence of n elements or words in a given document. The bag of words model that we've explored so far is nothing but an n-gram model where n is equal to 1. Let's now explore n-grams where n is greater than 1. Consider the sentence for you 1,000 times over. If we set n to 2, then the n-grams, called bigrams in this case, would be for you, youer, 1,000, 1,000 times and times over. Similarly, for n equal to 3, the n-grams or trigrams will be for youer, you 1,000, 1,000 times and 1,000 times over. Therefore, we can use these n-grams to capture more context and account for cases like not. Apart from capturing more context, n-grams have a host of other useful applications. They are used in sentence completion, spelling correction, and machine translation correction. In all these cases, the model computes the probability of n words occurring contiguously to perform the above processes. Building these n-gram models using scikit-learn is extremely simple now that we know how to use Count Vectorizer. Count Vectorizer takes in an argument n-gram range, which is a tuple containing the lower and upper bound for the range of n-gram values. For instance, passing 2, 2 as the n-gram range will generate only bigrams. On the other hand, passing in 1, 3 will generate n-grams where n is equal to 1, 2, and 3. While on the surface, it may seem lucrative to generate n-grams of high orders to capture more and more context, it comes with caveats. We've already seen that the BOW vectors run into thousands of dimensions. Adding higher order n-grams increases the number of dimensions even more, and while performing machine learning leads to a problem known as the curse of dimensionality. Additionally, n-grams for n greater than 3 become exceedingly rare to find in multiple documents, so that feature becomes effectively useless. For these reasons, it is often a good idea to restrict yourself to n-grams where n is small. In the last chapter, we learned about n-gram modeling. In n-gram modeling, the weight of a dimension for the vector representation of a document is dependent on the number of times the word corresponding to the dimension occurs in the document. Let's say we have a document that has the word human occurring 5 times. Then, the dimension of its vector representation corresponding to human would have the value 5. However, some words occur very commonly across all the documents in the corpus. As a result, the vector representations get more characterized by these dimensions. Consider a corpus of documents on the universe. Let's say there is a particular document on Jupiter, where Jupiter and universe both occur 20 times. However, Jupiter rarely figures in the other documents, whereas universe is just as common. We could argue that although both Jupiter and universe occur 20 times, Jupiter should be given a larger weight on account of its exclusivity. In other words, the word Jupiter characterizes the document more than universe. Weighting words this way has a huge number of applications. They can be used to automatically detect stop words for the corpus instead of relying on a generic list. They're used in search algorithms to determine the ranking of pages containing the search query, and in recommender systems, as we will soon find out. In a lot of cases, this kind of weighting also generates better performance during predictive modeling. The weighting mechanism we've described is known as term frequency inverse document frequency, or TF-IDF for short. It is based on the idea that the weight of a term in a document should be proportional to its frequency and an inverse function of the number of documents in which it occurs. Mathematically, the weight of a term I in document J is computed as the term frequency of the term I in document J multiplied by the log of the ratio of the number of documents in the corpus and the number of documents in which the term I occurs, or DFI. Therefore, let's say the word library occurs in a document 5 times. There are 20 documents in the corpus and library occurs in 8 of them. Then, the TF-IDF weight of library in the vector representation of this document will be 5 times log of 20 by 8, which is approximately 2. In general, higher the TF-IDF weight, more important is the word in characterizing the document. A high TF-IDF weight for a word in a document may imply that the word is relatively exclusive to that particular document, or that the word occurs extremely commonly in the document, or both. Generating vectors that use TF-IDF weighting is almost identical to what we have already done so far. Instead of using count vectorizer, we use the TF-IDF vectorizer class of scikit-learn. The parameters and methods it has is almost identical to count vectorizer. The only difference is that TF-IDF vectorizer assigns weights using the TF-IDF formula from before and has extra parameters related to inverse document frequency, which we will not cover in this course. Here, we can see how using TF-IDF vectorizer is almost identical to using count vectorizer for a corpus. However, notice that the weights are non-integer and reflect values calculated by a TF-IDF formula. We now know how to compute vectors out of text documents. With this representation in mind, let us now explore techniques that will allow us to determine how similar two vectors, and consequently two documents, are to each other. More specifically, we will learn about the cosine similarity score, which is one of the most popularly used similarity metrics in NLP. Very simply put, the cosine similarity score of two vectors is the cosine of the angle between the vectors. Mathematically, it is the ratio of the dot product of the vectors and the product of the magnitude of the two vectors. Let's walk through what this formula really means. The dot product is computed by summing the product of values across corresponding dimensions of the vectors. Let's say we have two n-dimensional vectors v and w as shown. Then the dot product here would be v1 times w1 plus v2 times w2 and so on until vn times wn. As an example, consider two vectors a and b. By applying the formula above, we see that the dot product comes to 37. The magnitude of a vector is essentially the length of the vector. Mathematically, it is defined as the square root of the sum of the squares of values across all the dimensions of a vector. Therefore, for an n-dimensional vector v, the magnitude mod v is computed as the square root of v1 square plus v2 square and so on until vn square. Consider the vector a from before. Using the above formula, we compute its magnitude to be root 66. We are now in a position to compute the cosine similarity score of a and b. It is the dot product, which is 37, divided by the product of the magnitudes of a and b, which are root 66 and root 38 respectively. The value comes out to be approximately 0.738, which is the value of the cosine of the angle theta between the two vectors. Since the cosine score is simply the cosine of the angle between two vectors, its value is bounded between -1 and 1. However, in NLP, document vectors almost always use non-negative weights. Therefore, cosine scores vary between 0 and 1, where 0 indicates no similarity and 1 indicates that the documents are identical. Finally, since the cosine score ignores the magnitudes of the vectors, it is fairly robust to document length. This may be an advantage or a disadvantage depending on the use case. Scikit-learn offers a cosine similarity function that outputs a similarity matrix containing the pairwise cosine scores for a set of vectors. You can import cosine similarity from sklearn.metrics.pairwise. However, remember that cosine similarity takes in 2D arrays as arguments. Passing in 1D arrays will throw an error. Let us compute the cosine similarity scores of vectors a and b from before. We see that we get the same answer of 0.738 from before. In this lesson, we will use TF-IDF vectors and cosine scores to build a recommender system that suggests movies based on overviews. We have a dataset containing movie overviews. Here, we can see two movies, Shanghai Triad and Cry the Beloved Country, and their overviews. A task is to build a system that takes in a movie title and outputs a list of movies that has similar plot lines. For instance, if we passed in The Godfather, we could expect output like this. Notice how a lot of the movies listed here have to do with crime and gangsters, just like The Godfather. Following are the steps involved. The first step, as always, is to pre-process movie overviews. The next step is to generate the TF-IDF vectors for our overviews. Finally, we generate a cosine similarity matrix which contains the pairwise similarity scores of every movie with every other movie. Once the cosine similarity matrix is computed, we can proceed to build the recommender function. We will build a recommender function as part of this course. Let's take a look at how it works. The recommender function takes a movie title, the cosine similarity matrix, and an indices series as arguments. The indices series is a reverse mapping of movie titles with their indices in the original data frame. The function extracts the pairwise cosine similarity scores of the movie passed in with every other movie. Next, it sorts these scores in descending order. Finally, it outputs the titles of movies corresponding to the highest similarity scores. Note that the function ignores the highest similarity score of 1. This is because the movie most similar to a given movie is the movie itself. Let's say we already have the pre-processed movie overviews as movie plots. We already know how to generate the TF-IDF vectors. Generating the cosine similarity matrix is also extremely simple. We simply pass in TF-IDF matrix as both the first and second argument of cosine similarity. This generates a matrix that contains the pairwise similarity score of every movie with every other movie. The value corresponding to the ith row and the jth column is the cosine similarity score of movie I with movie J. Notice that the diagonal elements of this matrix is 1. This is because, as stated earlier, the cosine similarity score of movie K with itself is 1. The magnitude of a TF-IDF vector is always 1. Recall from the previous lesson that the cosine score is computed as the ratio of the dot product and the product of the magnitude of the vectors. Since the magnitude is 1, the cosine score of two TF-IDF vectors is equal to their dot product. This fact can help us greatly improve the speed of computation of our cosine similarity matrix, as we do not need to compute the magnitudes while working with TF-IDF vectors. Therefore, while working with TF-IDF vectors, we can use the linear kernel function, which computes the pairwise dot product of every vector with every other vector. Let us replace the cosine similarity function with linear kernel. As you can see, the output remains the same, but it takes significantly lesser time to compute. The recommender function and the indices series described earlier will be built in the exercises. You can use this function to generate recommendations using the cosine similarity matrix. We have covered a lot of ground in the last 4 chapters. However, before we bid adieu, we will cover one advanced topic that has a large number of applications in NLP. Consider the 3 sentences: I am happy, I am joyous, and I am sad. Now, if we were to compute the similarities, I am happy and I am joyous would have the same score as I am happy and I am sad, regardless of how we vectorize it. This is because happy, joyous, and sad are considered to be completely different words. However, we know that happy and joyous are more similar to each other than sad. This is something that the vectorization techniques we've covered so far simply cannot capture. Word embedding is the process of mapping words into an n-dimensional vector space. These vectors are usually produced using deep learning models and huge amounts of data. The techniques used are beyond the scope of this course. However, once generated, these vectors can be used to discern how similar 2 words are to each other. Consequently, they can also be used to detect synonyms and antonyms. Word embeddings are also capable of capturing complex relationships. For instance, it can be used to detect that the words king and queen relate to each other the same way as man and woman, or that France and Paris are related in the same way as Russia and Moscow. One last thing to note is that word embeddings are not trained on user data. They are dependent on the pre-trained Spacy model you're using and are independent of the size of your dataset. Generating word embeddings is easy using Spacy's pre-trained models. As usual, we load the Spacy model and create the doc object for our string. Note that it is advisable to load larger Spacy models while working with word vectors. This is because the EN-core Web SM model does not technically ship with word vectors but context-specific tensors, which tend to give relatively poorer results. We generate word vectors for each word by looping through the tokens and accessing the vector attribute. The truncated output is as shown. We can compute how similar 2 words are to each other by using the similarity method of a Spacy token. Let's say we wanted to compute how similar happy, joyous, and sad are to each other. We define a doc containing the 3 words. We then use a nested loop to calculate the similarity scores between each pair of words. As expected, happy and joyous are more similar to each other than they are to sad. Spacy also allows us to directly compute the similarity between 2 documents by using the average of the word vectors of all the words in a particular document. Let's consider the sentences from before. We create doc objects for the sentences. Like Spacy tokens, docs also have a similarity method. Therefore, we can compute the similarity between 2 docs as follows. As expected, I am happy is more similar to I am joyous than it is to I am sad. Note that the similarity scores are high in both cases because all sentences share 2 out of their 3 words, I and am. Congratulations on making it to the end of the course. In this course, we learned about various feature engineering techniques for natural language processing in Python. We started off by computing basic features such as character length and word length of documents. We then moved on to readability scores and learned various metrics that could help us deduce the amount of education required to comprehend a piece of text fully. Next, we were introduced to the Spacy library and learned to perform tokenization and lemmatization. Building on these techniques, we proceeded to explore text cleaning. We also learned how to perform part-of-speech tagging and named entity recognition using Spacy models and had a sneak peek at their applications. The third chapter was dedicated to n-gram modeling. We also explored an application of it in sentiment analysis of movie reviews. The final chapter saw us covering TF-IDF vectors and cosine similarity. Using these concepts, we built a movie and a TED Talk recommender. The final lesson gave you a sneak peek into word embeddings and their use cases. This, by no means, is the end of the road. Once you're done with this course, it is highly recommended that you take the following courses, also offered by DataCamp, to muscle up your skills further.